So we talk about the subspace, right? So here's like a very important subspace that which will be used in the later discussion. Okay, it is called null space. Okay, it is defined over a matrix. Okay, and this matrix, okay, is not necessarily square matrix. Okay, A is an n times n matrix, but n and n are not necessarily the same. Okay, so we let n of A denote the set of all solutions to the homogeneous system Ax equal to 0. Okay, so NA is defined to be all the possible vectors that Ax, and this can be verified very easily that this is a subspace. Okay, obviously that if you let X to be 0 vector, okay, it satisfies this property. So 0 is in this null space, obviously. So this null space is not empty, right? And if X is in this null space, Cx must be in this null space too. Okay, if X1 is in this null space, X2 is in this null space, then X1 plus X2 must be in this null space as well, right? It's very easy to verify. Like NA is a subspace of R. So NA is called null space. Okay, this is like actually let's look at okay. Then A to be this one. Okay, it's a 2 by 4 matrix. 2 by 4 matrix. So obviously, if you want to solve Ax equal to 0, okay, you just try to use the Gauss-Jordan elimination, okay, and to think that this is a process that relatively easy. Okay, we talk about this in chapter 1. Okay. So this means what? This means okay. If we name the x1, x2, x3, x4, okay, how should I say that? It means x1 plus 0 times x2 minus x3 plus x4 equal to 0. Okay, and then x2 plus 2x3 minus x4 equal to 0. Okay, so we have these two formulas. Okay, or we can, if we let x3 to be s, s4 to be t, then x1 will be written like this, x2 will be written like this. So in other words, we can write it like that. And then if we try to separate the s term and the t term, this is what we get. And you can see that we can get S out to be like this, T out of the second term like this. So in other words, okay, the null space is a linear combination of these two vectors, right? It's a linear combination of these two vectors. Okay. I mean, if you try to understand it, it's like remember we talk about like Ax equal to 0. Okay, this is your A, this is your X. What does that mean? if x is like x has to be like x1, x2, xn, right? It is this is n times n. Okay, remember what do we what we talk about? Okay, it means what should I say? Like these are column vector. Okay, it means x1 times the first column plus x2 times the second column plus blah blah plus xn times the nth column. We add up these columns to be 0. Right? This is another way to understand it. Okay? So it means like null space basically is like to give like a matrix. Okay, you use the column vectors in this matrix. Okay, linear combine this column matrix and try to get a 0 vector. Okay, so that's your constraint. So how do you do it? Okay, that's another way to rationalize this null space, because like later on this type of stuff, okay, will help you to have a better understanding of this. So we will come back to this null space later. Okay, we discuss the dimensionality. Okay. And previously, like when we discussed this null space, you can see like this thing, right? Like two vectors span a particular space, right? Two vectors span a particular space. So now we formally define like span of a set of vectors. Okay. Given like n vectors in a vector space, the sum of the form alpha 1 b1 plus alpha 2 b2 plus blah 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 plus alpha n bn, where alpha 1, alpha 2, alpha 2, alpha n are scalars. They are any scalars, any real numbers. Okay, it's called a linear combination of b1, b2 up to bn. Okay, so using this definition, you can see like the null space here is a linear combination of these two vectors, right? So the set of all linear combination of b1, b2 up to bn, we denote it as span b1 to bn. So that's the notation, and we call it just a span of these vectors. So actually, the span of any set of vectors is a subspace. Okay. So if b1 to bn are vectors of a vector space V, okay, because they are vectors, so they obviously belong to certain vector space. Okay. So span b1 to bn is a subspace. Okay. So S just denoted as span b1 to bn. So first, this S is not empty because alpha 1, alpha 2, we just let this alpha I to be 0. So we know 0 vector is in this span, right? And also, okay, if a vector is in this span, now this vector can be written as in this form. Then CV will also be able to be spent, be represented by like a linear combination of D1 to Dn, right? Basically just like multiply this everything by constant C. So originally we have alpha 1, alpha 2, up to alpha n. Now you have C alpha 1, C alpha 2, blah blah blah, C alpha n. That's it. Right? And also if V and W are like can be written in this form. Okay, so V is written as like this. W is can be written like this. So it's like alpha 1, alpha 2, blah blah. This is beta 1, beta 2. Then V plus W can be written like that, right? So in other words, V plus W is also in this span. In other words, this span is the subspace of the vector space. Okay? So here, okay, the null space of A equal to this one is a span of vector, these two vectors. We talk about this. Let's say this is the span of these two vectors. So I already used this example. Okay. So in R3, the span of E1 is alpha 0, 0, where alpha is any number. This must be the subspace of R3. That's very easy to verify. Okay. The span of E1, E2 basically is alpha beta 0. Okay. You know the E1, what the definition of E1, right? E1 is the 1, 0, 0. E2 is 0, 1, 0. The unit vector of a particular dimension. Okay, E1 is the unit vector of dimension 1. E2 is the unit vector of dimension 2, and so on. Okay. So this, when you linear combine these unit vectors, obviously it's just like that. So they are obviously the subspace of R3. Assuming that it's a three-dimensional. So here, okay, the set V1 to Vn is a spanning set for V if and only if every vector in V can be written as a linear combination of V1, V2, Vn. Okay, so this is a if and only. First, this is definition, so I don't need to prove that. But this definition is English expression is a if and only. So we say like if every vector in V can be written as a linear combination, okay, in other words, any vector in V, okay, belong to like a span of V1 to Vn, so we can say V is a subset of this one. Okay? So we'll put it another way. V1 to Vn, the linear combination of these vectors is sufficiently large to cover this set of V, set. So the following will be some questions that you need to consider. Okay. Which of the following are spanning sets for R3? Okay, the first one is E1, E2, E3, 1, 2, 3. The 1, 2, 3 is the additional vector. Okay, so you have like, so obviously like if you try to rationalize like any vector in R3 can already be represented by like the linear combination of E1, E2, and E3, right? So if you put one additional vector there, it doesn't hurt, right? It doesn't hurt. So yes, okay. The R3 is a linear, is a spanning set of E1 into E3. Yes. Okay. Actually, it's a little bit too much. You don't need those 4 vectors. You need only 3. Maybe E1 into E3. Or, okay, you can get rid of one of the E1 into E3 and keep the E1 into 3. The reason, I mean, for that, we need to, we need to improve that. But basically, we know that if you keep all those vectors there, it's more than enough to cover R3, right? So, basically, this is a reason, as I said, you just need 0 and 3. And then the other thing, okay, 111, 110, 100. This one, okay, you need to verify if this, ABC can be spanned. ABC, where A and B and C are 3 arbitrary numbers. So this pretty much represents an arbitrary vector in R3. So this arbitrary vector in R3, okay, we want to see if it can be spanned by these 3 vectors. So in other words, we want to solve, okay, if we try to write it like in more formal way, okay, it's going to, we are going to have this system linear equation. Okay, so the first column, 111 times alpha, plus the second column, 110 times beta, plus the third column, 100 times gamma. Okay, the combination, okay, of this linear combination of this will be ABC. So we want to show this system is solvable, right? We want to show this system is solvable. So if I give you this, how to make sure it's consistent or it's solvable? Here, okay, we do not know ABC. Because ABC are arbitrary numbers. And the alpha, beta, gamma are, we want to make sure there is one combination for every given ABC. How do we do that? It looks like you have 6 unknown, but you have only 3 equations, right? But in fact, what you only need is to make sure this matrix, okay, has inverse. Okay, because if this one has an inverse, then say this is matrix A, okay, then you multiply A inverse on the left hand side. This thing is gone, right? And the right hand side you multiply A inverse with alpha, with ABC. Well, it's going to create something we don't know, but that's not important. The important thing is that, okay, if this matrix has inverse, we must be able to solve this, linear equations for any given ABC value, right? Right? So it comes down to the fact that whether or not that matrix has an inverse. Okay, and we talk about inverse of the matrix like last chapter already, right? Okay, so I think that I'll stop there. So more example, okay, which of following are spanning sets for R3? first one, okay, 101010. Okay. This one, okay. Intuitively speaking, R3 has three freedom, degree of freedom, right? And here you only have two vectors. Now, if you want to use like a linear combination of two vectors to create something that has like a freedom of degree 3, that's impossible. But yeah, we haven't really formally talked about dimension concept yet, so we cannot use that here. Okay, unfortunately. But we know like we can do this, right? Okay, so it's alpha times the first column plus beta times the second column equal to something. So basically this is just an example. We want to show that it's not possible. So we give an arbitrary vector which is 102. Okay, there are a lot of examples that you cannot spell. This is just one such example because like if you in the previous case we can do it because like the matrix is a square matrix. This one we cannot directly solve. We have to have a particular vector on the right hand side. Okay. Otherwise, this one we cannot discuss. This has an inverse because it's not a square. It's not square. But it should be relatively easy to find something that is like not so. Okay. So basically, this just means that the first value to be alpha, the second value to be beta. So alpha is 1, beta is 2. And then the third value is alpha again. But alpha cannot be 1 and 2 at the same time. So we are in trouble. So any such similar example, you have the case. As long as the first element and the third element are different, you have this inconsistent case. Okay. So that another example: 1, 2, 4, 2, 1, 3, 4, negative 1, 1. Verify this. Okay, is solvable for every A, B, C. So again, we try to write it like that. And in this case, okay, because it's a square matrix, okay, we don't have to find the A, B, C. You can directly look at like this matrix and see it's like it has an inverse. And whether or not a matrix has inverse, from the discussion of the last chapter, we know that we just need to check the determinant of this matrix is non-zero, right? If the determinant of this matrix is non-zero, it has an inverse. Okay, it has an inverse. And then we can do that computation as I said earlier. Okay, multiply both sides from the left-hand side with A inverse. Okay. But now we have like something that is a little bit more interesting. Okay. Because previously, all the examples we are talking about is they are about like the vector space, like traditional vector space. Okay. Again, like as I said, like the linear algebra deal with not only just those vector space, but also like
something that does not look like a vector space. So for example, like P2. What is P2? Everybody remember? It's a set of all polynomials with a degree up to 2, right? 就是那个多项式，那个就是那个 degree 啊，就是它那个次方最多2次这样子的那个所有的多项式的值。Okay, 这是 P2。Then we want to prove that 1 minus x2, x plus 2, okay, and x squared, okay, split P2. First, okay, what we are asking is something like this. Given any combination of A and B and C, we want to prove that we can find alpha, beta, and gamma to solve this. Right? Right? So this is like underline what we want to do. Okay? But it's a little bit complicated, right? So let's try to write it kind of like a linear algebra, shall we? Okay? So we treat this one as ABC. Okay, just like the previous example that we had. Okay, ABC. So in other words, this one represents 1. This one represents x. This one represents x squared. Right? Right? Or, so if we write it like that, okay, we can sort of consider this 1 minus x squared, x plus 2, and x squared, sort of like the vectors, like that, as well. So it's going to be alpha. Right? Right? You try to represent each of these like what we have here. The first value represent coefficient for 1, the term 1. The second term represent coefficient for the term x. The third value represent coefficient for the term x squared. If you use the same rationale to write the left hand side, it looks like that, right? can be written as right? Right? So in other words, this thing, like this, equal to that. Right? So to show this is like doable, it's relatively easy. We just need to make sure we can find the inverse of this matrix, right? 这还好玩，可以啊。就是 although it does not look like linear algebra, but after we carefully transform it into vector shape, okay, it is linear. It is linear algebra. Okay. It's a very interesting problem to consider. Actually, a lot of problems, okay, although they do not look like vectors, but they can be treated as vectors. Okay, just like this one. Okay, the a plus bx plus cx squared. Okay, it doesn't look like a vector. We can treat it like that. Okay, later on we talk about basics. You will get a better idea, better understanding what we are doing here. Okay, we are actually trying to do what should I say, the basis transformation. Okay, instead of point out the basis, just or the tool part, basis tool. You get it. Oh, okay. So we are done with finding done with subspace, and we can move on to the linear independence. So to discuss linear independence, first we need to know the definition of linear independence. Okay. So given like a set of vectors, we want to be okay, they are said to be linearly independent if alpha 1 b1 plus alpha 2 b2 plus blah blah plus alpha n bn equal to 0. This equation has exactly one solution: alpha 1 equal to alpha 2 equal to blah blah equal to alpha n equal to 0. So other than this 0, or you can say it's a trivial solution. Other than this trivial solution, there is no other solution. Okay, if this is the case, we say B1 to Bn is set of vectors is linearly independent. Okay, so we can easily show, for example, the vectors 1, 2, 2, 1 are linearly independent. Why? try to write it like this, and you try to solve it, it means what? It means alpha plus 2 beta equal to 0. And 2 alpha plus beta equal to 0. Okay? You can do a very simple calculation and find that the only possible solution is 0 and 0. Okay. Although I'm trying to tell you something in the following, okay, I want you to consider this as a matrix format. Okay, it means what? It means after all, the linear algebra is about matrices. Okay, so we should always consider the problem, okay, in the form of matrix. So this one, okay, if you write it in a matrix, okay, it's going to be 1, 2. It appears as the first column, and the second one, the 2, 1 is appear as the second column. It's alpha beta. So we are writing that in a form of matrix, right? In what situation you are going to have like one single solution here? If I write it in a matrix, because it's happen to be square, you can take an easy guess. It is when this matrix has an inverse, right? When this matrix has inverse, you have only one solution and only one trivial solution where alpha and beta are both 0. Think about that. We will have further discussion here. Okay, let's take a 10-minute break. We'll come back and continue our discussion.